A spacecraft can be built for years, tested by hundreds of people, and still be sent off course by a unit conversion. That is what happened to NASA's Mars Climate Orbiter. The hardware was real, the propulsion system worked, the navigation calculations looked reasonable, but two teams used different units to describe the same tiny push from the spacecraft's thrusters. One side used pound force seconds, the other expected Newton seconds. That mismatch followed the spacecraft all the way to Mars. I want to walk through this case carefully, because the important lesson is not simply that someone forgot to convert pounds to newtons. The deeper lesson is how a small disagreement at an interface can become a major trajectory error when the system is separated by millions of kilometers. Mars Climate Orbiter was launched by NASA on December 11, 1998. Its mission was to study the Martian atmosphere, observe weather and dust activity, and help relay communications for other Mars missions. The spacecraft was managed through NASA's Jet Propulsion Laboratory, while Lockheed Martin Astronautics built the spacecraft and supplied important ground software. The plan was for the orbiter to reach Mars, pass into orbit, and then use a technique called aerobraking. Aerobraking uses repeated passes through the upper atmosphere to remove orbital energy. Instead of carrying enough fuel to perform every part of the orbit change with engines alone, the spacecraft would use the atmosphere as a controlled source of resistance. That made accurate navigation especially important. The spacecraft could tolerate a carefully planned atmospheric pass, but the difference between a safe altitude and an overly low altitude was not something the mission could casually absorb. During its journey from Earth to Mars, the spacecraft performed trajectory correction maneuvers. These were controlled firings of its small thrusters. Each firing changed the spacecraft's velocity by a very small amount. On Earth, that change would seem insignificant. In interplanetary navigation, however, a small velocity change can alter where a spacecraft will be weeks or months later. Imagine pushing a shopping cart just slightly to one side at the beginning of a very long hallway. Near the starting point, the difference is hard to notice. Farther down the hallway, the cart may be several meters away from the intended path. A spacecraft behaves in a more complicated way, but the principle is similar. Every correction has to be measured, modeled, and carried forward into the next prediction. That is where the unit mismatch entered the story. The thruster data produced by software connected with the spacecraft operations were expressed in pound force seconds, sometimes shortened in engineering language to pound seconds. Pound force second is a unit of impulse. Impulse is force multiplied by time, and it tells navigators how much momentum a thruster firing adds or removes. The navigation software used by the JPL team expected the metric unit, the Newton second. Both units are legitimate. Neither one is inherently inaccurate. The problem was that the software systems did not agree on which unit was being exchanged. 1 pound force second is approximately 4.45 Newton seconds. So if a value of 1 was passed from one system to another without conversion, the receiving system did not see a slightly different value. It interpreted the impulse as a force about 4.5 times larger or smaller than intended, depending on which direction the conversion was missed. In this case, the ground software and the navigation process treated the information differently. The spacecraft's actual thruster impulses were not the same as the impulses assumed by the navigation calculations. The result was a growing disagreement between where the navigation team believed the spacecraft was going and where its physical trajectory was taking it. This is the part that can feel counterintuitive. The thrusters were not firing wildly. The software was not necessarily producing obvious nonsense. The spacecraft was still communicating during much of the journey, and the numbers could look like normal engineering values. A unit error does not always create a giant, impossible number. Sometimes it creates a plausible number with the wrong meaning. That is much harder to notice. If a sensor reports 30 and nobody knows whether 30 means meters or feet, the number itself does not announce the problem. It can pass through a computer, appear in a table, and influence a decision before anyone asks the most basic question, 30 what? The Mars Climate Orbiter case involved that kind of semantic gap. The data had a numerical value, but the meaning attached to the value was not consistently preserved between teams and software systems. On September 23, 1999, Mars Climate Orbiter reached the point where it was supposed to conduct its Mars orbit insertion. The spacecraft passed behind Mars as planned, and the mission team expected communication to resume after the maneuver. It did not. The spacecraft was not recovered. The official investigation concluded that the vehicle had approached Mars on a trajectory that was too low. The reconstructed path placed the spacecraft near an altitude of about 57 kilometers above the Martian surface, rather than the planned altitude of roughly 140 to 150 kilometers. At that lower altitude, the atmosphere posed a completely different engineering environment. NASA could not establish with certainty exactly what happened to the spacecraft after communication was lost. The evidence pointed toward an atmospheric passage that was too low, with the spacecraft either unable to survive that encounter or leaving the intended mission path. What the investigation could establish more confidently was the chain leading up to it. The navigation process received thruster impulse information in a unit system different from the one its calculations expected, and that discrepancy was not caught before the final approach. It is tempting to describe the entire event as a single line of code. That description is too narrow. The wrong unit may have been present in software, but the larger failure was at the boundary between organizations, tools, and assumptions. Lockheed Martin's software could be internally consistent with the units it used. JPL's navigation software could also be internally consistent with metric units. Each team might believe its own calculations were correct. The danger appeared between the systems, where the interface did not make the unit impossible to misunderstand. This is why engineering teams talk about interfaces as contracts. An interface does not merely transfer a number. It transfers a number, a definition, a scale, a direction, a timestamp, and a set of assumptions about how the value should be interpreted. If the number crosses a boundary without those details, the receiving system may process it perfectly and still produce the wrong result. Here is a simpler analogy. Suppose one workshop sends a cutting list to another workshop. The first workshop measures in centimeters. The second workshop assumes inches. Every measurement is written neatly. Every cut is made accurately. Every worker follows the instructions. Yet the assembled structure will not fit because the disagreement was not about craftsmanship. It was about the meaning of the measurements. Mars Climate Orbiter was the spaceflight version of that problem, except the pieces were not sitting in two workshops. One was moving through space, and the error accumulated over time. There is another reason this case matters. In many systems, the quantity being measured is not the final thing anyone cares about. The final concern is the consequence. For Mars Climate Orbiter, the critical consequence was position relative to Mars during arrival. The unit mismatch did not directly push the spacecraft into a low approach in one dramatic moment. It distorted the model of earlier corrections. That model then influenced later navigation decisions. By the time the error became a trajectory problem, the original source was far away in both the software architecture and the mission timeline. This is a form of risk transfer. A small uncertainty in a low-level component can become a high-consequence uncertainty in a higher-level decision. The component may be a data field. The next layer may be a navigation estimate. The next layer may be a maneuver plan. Finally, the system depends on the predicted arrival path. At every layer, the output can look reasonable enough to pass forward. That is why end-to-end verification matters. Testing one program in isolation is not the same as testing whether two programs agree about the world. A calculator can give the correct answer to the question it was asked, even if another team believed it had asked a different question. For a mission like this, a strong verification process would need to test more than arithmetic. It would need to test the complete path of the data, where the value originated, what physical quantity it represented, how the unit was encoded, how it was converted, how it was stored, how it was transmitted, and how the receiving software interpreted it. It would also need independent ways to check the result. That might include dimensional analysis, redundant trajectory calculations, simulated maneuvers, or an interface specification that explicitly identifies units rather than leaving them in a team convention. These are not glamorous safeguards, but they are exactly the kinds of safeguards that protect complex systems from ordinary mistakes. The official investigation into the Mars Climate Orbiter loss identified the unit mismatch as the direct technical cause and also pointed to broader process problems. The important boundary here is that the public findings support a conclusion about incompatible units and inadequate detection of the discrepancy. They do not justify inventing a dramatic story about one person, one warning, or one moment of carelessness. The evidence is about a system of software, procedures, communication, and review. Assigning the entire outcome to an individual would hide the engineering lesson. If a critical interface allows two teams to use different meanings for the same field without an automatic alarm, then the system is relying too heavily on memory and informal understanding. Good engineering tries to move that burden away from memory. A unit should be visible in the interface. Better still, it should be encoded in a way that software can check. A conversion should happen in one clearly defined location, not in a vague assumption shared by people who may work with different tools. A test should compare the output of one system with the expected output of the next system, and a reviewer should be able to trace a physical quantity from the hardware, through the software, into the final mission calculation. The Mars Climate Orbiter case also shows why metric versus imperial arguments are often framed too casually. The real issue is not that one side used an old-fashioned unit and the other used a modern unit. Aerospace has worked with many unit systems. The real issue is an uncontrolled transition between them. A conversion can be safe if it is explicit, checked, and documented. It becomes dangerous when the conversion exists only in someone's expectation. Even familiar units can cause problems. A value in meters can be misunderstood as kilometers. A temperature can be interpreted as Celsius instead of Fahrenheit. A pressure can be treated as absolute instead of gauge. The numbers may all look normal. The physical meaning is what changes. In spacecraft navigation, physical meaning is the entire game. When I look at Mars Climate Orbiter, I do not see a lesson that says engineers must never make mistakes. That standard is impossible. I see a lesson that says important systems must be designed so that one ordinary mistake cannot quietly travel through the entire chain. The goal is not perfect human attention. The goal is resilient architecture. That means clear interface definitions, automated unit checking, independent calculations, realistic end-to-end tests, and a culture where someone can ask a basic question without assuming the answer is obvious. Why were the units not converted? Where is that conversion performed? What happens if the value arrives in the wrong scale? What independent measurement would reveal the error? Those questions sound simple, but simplicity is exactly why they are useful. They reach beneath layers of specialized language and return to the physical reality of the machine. A thruster creates impulse. Impulse changes velocity. Velocity changes trajectory. Trajectory determines altitude. Altitude determines whether the mission can perform its planned orbit insertion. When each link is stated plainly, the importance of the unit becomes impossible to dismiss. Mars Climate Orbiter was designed to explore Mars, but its most lasting contribution may be here on Earth, inside engineering practice. It reminds us that a system can fail without a broken part, without an obviously absurd calculation, and without a single dramatic malfunction. A spacecraft can be lost because two correct-looking systems disagree about what a number means. The lesson applies to spacecraft, aircraft, medical devices, power networks, software services, and even the spreadsheet on a desk. Whenever information crosses a boundary, the unit and definition must travel with it. If you found this case useful, like the video and follow for more carefully researched engineering history. Then comment with the first unit mismatch you remember seeing in a real system, because the best way to prevent these failures is to make the invisible assumptions visible.